Process is very straightforward because it's consistent. All right, we have some assumptions. Now, these are textbook assumptions that, like in an AP stat class in the high school, they actually have to state these assumptions. They have to have them memorized, state them on an exam in order to get credit. And as far as I can tell, that's the only reason why they have to state them, to get credit, because you don't really need to actually list out any assumptions as long as you're aware of them, right? So when you're testing a claim about a proportion, there needs to be randomization in the study. So it has to be random, but that's the thing. All of our studies are going to be random. They're going to involve randomization. So that makes this one kind of irrelevant, right? Because all of our studies are going to have randomization, so we're not worried about this. All studies random, so irrelevant. All right, so you don't have to worry about that one. Now, if you're doing the project, yeah, I guess you kind of have to worry about it, but you wouldn't have to worry about it when you're actually running your hypothesis test, because you will have already collected your data randomly through the survey process. All right, so even in that context, it's still irrelevant because you've already randomized. All right, you selected your individuals at random. Right, so it's already accounted for. Right, the 4 conditions for a binomial distribution are satisfied. Right, so let's just think about that for a second. There are a fixed number of trials. That'll be your sample size. Fixed probability, well, that's what we're looking for. Independent events, well, what one person tells you in the results of a survey is going to be completely different from everybody else. You can't just use up the answers. Like if you were to say, how many siblings do you have? And they say 3, that doesn't mean other people can't have 3 siblings. So that's not going to be a problem. And then 2 outcomes. All right. So and you might look at 2 outcomes as yes or no, up or down, left or right, whatever. It's more like the answer you're looking for versus the answer you're not looking for. All right. So, like if you asked individuals, if the point of your study was, this day and age people have less siblings than they used to, then you would just have some cutoff number where you would say you're either more or less in terms of the number of siblings. Pick the number 2, for example. You either have more or less than 2 siblings, right? It's binary, right? Binomial. So bottom line is these 4 conditions are going to be satisfied in your study in some capacity, right? So really, you're not going to have to worry about that one either, right? The third one, you're not going to have to worry about because you got to do these calculations anyway in order to find what we call the p-value. Right? So, and that's all going to be included in the calculator process. So, long story short, we're not worried about any of these assumptions because it's all either going to be, if I give you a word problem, it's all going to be accounted for in the word problem. Or if you're doing a study, it's all going to be accounted for in the development of your study in and of itself. Right? So, what we do is we jump right to step 1 and state the null and alternative hypotheses. All right? The null hypothesis always involves an equal sign, right? So again, we're always looking to quantify. So in your null hypothesis, you're going to say that the population proportion is equal to something, whatever the question's asking you or whatever you decide, right? So some of the popular questions talk about majorities versus minorities. Majority is greater than 0.5 or 50%. Minority is whether or not you're a white person. No, it's less than 50%. Okay? That's the thing, because people, I'll tell you right now, on tests, this is the thing that people screw up most frequently. I'll say, test the claim that a minority of voters supported the most recent decision by the elected official. And the result that the student produces will say, it is true that minorities supported the president. And I'm like, that's not what the question was asking, right? It's not an ethnic thing or a religious thing or anything like that. It is a simple question of more than 50%, less than 50%, all right? So this is one of those terms where you have to kind of put aside your own experiences outside of the classroom and just look at it as another math word, all right? And if there was a way around it, I would use that way around it. But this is such an integral part to statistics, that these two terms, that it just has to be here, all right? So majority, minority, all right? Major, minor, all right? So very important. Anyway, but you can see that both of those expressions have inequalities. One has a less than symbol and one has a greater than symbol. So any discussion about minority or majority is going to be corresponding with an alternative hypothesis, not a null hypothesis, right? Because it doesn't have an equal sign in it. And it's as simple as that. You'll read through a problem and say, doesn't have an equal sign, must be an alternative, right? Sometimes they won't tell you anything about the null hypothesis. You kind of have to figure it out on your own. But that's actually pretty easy. It's probably the easiest part, so I'll share that with you as we go. Step 2 is going to be identifying the level of significance, which is the alpha value, right? Most of the time, if not all the time, I'll say 99.5% of the time it's given to you. Like in a problem, I'll always give it to you on a test, right? Because honestly, answers vary when I don't give the alpha value, because if you have the liberty to choose it on your own, then I have to make 3 versions of an answer key, and that just work. I don't bother with that. So I just give you the alpha value. But you might see problems in textbooks, online resources, things like that, where they don't give you the alpha value. If that's the case, you just go with 0.05, right? I looked into why this was selected. I couldn't find anything that was more intelligent of an explanation than what I found, which was researchers have determined that a mistake in an experiment occurs about 1 in 20 times, which is 5%. And I was like, wait, what? So what do? They just ran a study like 20 times, and they're like, I only screwed it up once. So we'll go with that. Make that the rule, Charlie. Write it down. That's not how it goes. My explanation for it, which I have not seen anything to support, but it seems to make sense, is that when we're dealing with unusual values in probability, we're looking for the middle 95% of a normal distribution, right? Middle 95%, 2 standard deviations away from the mean, which leaves us 5% left over, right? So that 5% constitutes the unusual values. So if we're talking about alpha representing the amount of possible error and unusualness could correspond with one another. So I would say that 0.05 comes from the idea that we want to stay away from being unusually low. All right, 0.05 would be the unusual probability. So if we can keep it in that interval, then we're in good shape. Because again, we're talking about the probability of making a mistake. I want the probability of making a mistake to be unusually low. If I told you that on any question that you attempt on a test, that your probability of getting it wrong is going to be less than 0.05, I'd like to think you're feeling pretty good about that. The probability of you getting it wrong is less than 0.05, less than a 5% chance. That means that if you attempted that same problem 20 times, you'd only screw it up once. That's not bad, all right? Now, it depends on the question, of course, but that's not bad, all right? Now, this is a critical piece of information. If P is less than alpha, we reject the null hypothesis. That's for every single hypothesis test that we work on, all right? Because again, P is the P value is the probability that we're making a mistake. alpha is their cutoff of how much error we're willing to allow. If we're in that safe zone, then it's okay to reject the null hypothesis, because what it's telling us is that rejecting the null hypothesis, it's not a mistake to do so. All right? We're rejecting it correctly. All right? Yeah. Just trying to think. There was something else I wanted to say about that, and I had it, and I lost it for a sec. It'll come back. Oh, the conclusion. Most people don't like this, like what I'm about to say, but I decided a long time ago that I don't care, because consistency is a good thing when it comes to this. And it may seem like, man, he's really nitpicky and very particular about the way he wants his answer. And really, if you think about it, that's probably the only thing I'm nitpicky about. That and labeling graphs. Okay, so two things that I'm nitpicky about. But structuring your conclusion this particular way, it really, I mean, I've gone in different directions before. It really streamlines the process. Because what happens is, if people are left to their own devices to state a conclusion using their own brand of logic, things get out of control pretty quickly. And what happens is, you, on a test, you write a conclusion that you think is beautiful. Oh, it makes perfect sense in the world. And me, being a person who was born in logic, you know, like, I look at it and I say, well, that doesn't follow. I mean, that's not true in all cases, so I have to take off credit. All right? So I'm looking at it through a mathematical lens, and you're looking through it as, you know, well, it's common sense. It's all in there. Pretty much, I mean, I got the point across. It's not about getting the point across. It's about being logically accurate. All right? So follow this template, or you lose credit. All right? It's the only time I ever really say anything like that in any of the classes I teach. Usually it's, pick the method you like the most. Right? For this one, it's do it this way, or you're going to lose points. And that's for test or for project. It does not matter. All right? So let me explain what it means. And this is a universal template. It works for all the hypothesis tests. In parentheses is your adjustment to whatever the statement is. All right? So there is insufficient evidence or sufficient evidence. And so usually somebody's like, well, could I use enough instead of sufficient? I say no. Why? Because I just told you to follow my template. All right. That part, the sufficient versus enough, that actually isn't me. That's the American Statistical Association approved language for a statistical analysis. So if you read any journal, medical journal, engineering journal, whatever, that involves a statistical study, any conclusion for a hypothesis test, you'll always see that language in there. All right. So it's just the way I structured it that might be a little bit different. All right. So there is either insufficient evidence or sufficient evidence, depending on the outcome of your study, to reject the claim that, and then what we do is we state the null hypothesis in words. All right. That's usually pretty easy, because most of the time the null hypothesis is either flat out given to you, or it's related closely enough to the alternative that you can just adjust the alternative hypothesis that's given to you in the problem, and you'll have the null. All right, so it's very, very easy. Right? It doesn't seem like it would be at this point, because we haven't really done anything with it at the appropriate level. Thank you, sir. Yeah, no problem. At the 0.10, 0.05, or 0.01 significance level, so whatever is either given to you in the problem, and on the off chance that it's not given to you, you just use 0.05. Therefore, the claim that, and then you state the alternative hypothesis in words, is either going to be true or false. All right. The second sentence is not always necessary, because sometimes the question is not even asking about the alternative hypothesis. Sometimes it's only asking about the null, in which case the second sentence would be irrelevant. However, if you include the second sentence, I'll never take off credit because it'll still be correct. It's not something I'll be interested in. But I mean, as long as you don't write anything incorrect on paper, you're not on the hook for it. So put it in there if you want to have like muscle memory, to the point where you're not going to accidentally forget to leave it to include it when you need to have it there. I leave that up to you though. But you'll see what I'm talking about in 3, 2, 1. It's always pretty alarming when you see one problem and then an entire sheet of paper to write the solution for that one problem. Yeah, it's only because I'm gonna write some notes and put some screenshots in here. So now, full disclosure, if we had to do this by hand, it would take the whole page, and I used to do it that way, but I've definitely streamlined the process because I'm trying to. Honestly, I don't know if you're picking up on my signals. I'm trying to encourage people to do the project instead of taking the test. So with that in mind, the streamlining of these hypothesis tests are not designed necessarily for you to answer a bunch of different questions on a test related to hypothesis testing. It's more so that you could design your own study. All right, but you will be well prepared for any test I give you. But I'd rather you write a report because it's more meaningful for everyone, But some of us, we don't like doing that, and that's okay too. All right, so on the test, you're going to see that there's going to be a variety of multiple choice questions that are related to the sampling that we talked about last class. And then out of the 5 hypothesis tests that we're going to learn, I'm going to put 2 on the test, all right, that you'd have to perform yourself. All right, so I won't put all 5, but I'll put 2 of them. Will you tell us which ones in advance? No. Anyway, so it's claimed that apples are the most delicious fruit on the planet. I don't know who made that claim, but it was claimed by someone. You did, okay? So that's where it came from. So, and of course, it depends. I mean, it's a poorly worded question, obviously, because what kind of apples are we talking about here, and for what purpose? Because I mean, I accidentally chomped on a Granny Smith once, thinking it was something else. I almost chipped a tooth, and I squinted for like a good. It was like eating a lemon. So I was like, all right. So it definitely depends on the apple. All right. To test the claim, let us determine if the majority, keyword, majority of the population responds apples when asked what they think the most delicious fruit is. A sample of 4,500 people are selected and polled randomly. It is determined that 2,475 people chose apples as the most delicious fruit. Using a 0.05 significance level, test the claim that the majority of the population finds apples to be the most delicious fruit. All right, so first thing I'm going to do is identify the hypothesis test that's appropriate. Now, I see the word majority, which means that we're dealing with one population proportion. Now, this concept of one population proportion extends beyond just a discussion related to majority and minority. It could be a comparison to any percentage. Like, I could say that the percent of people who like apples is more than 25%, more than 30%, whatever percent I want. So comparison, I'll say, as soon as my pen starts working, involving only one proportion. All right, and just FYI, we use proportion and percentage interchangeably. All right, I try to stay away from using percent in this because if I say comparison involving only 1%, a person might look at it and say, wait, 1% is in like one with a percent symbol after it, or one value that is a percent of a population, right? So one proportion, I think, clarifies that a little bit. So anyway, we know that that's the deal. Now let's actually go to the calculator and see what the story is here, because the calculator is going to help us kind of make our way through this. Oh. Whoever else is teaching stats in this room is pretty much in lockstep with us. All right, so you're going to go to the stat test menu. So stat followed by tests. It's really the one menu related to statistics that we haven't gotten into yet. All right, so we're going to be living out of this menu for this, really the rest of the course, I guess. Yeah, because if you scroll down this list, you can see that there's a ton. Wait, I have two open? Why do I have two open? Yeah, well, whatever. Get out of here. All right. Yeah, so if you scroll down, or scroll up to get to the bottom, you could see that after 0, which is the 10th value, you got even more. So 1, 2, 3, 4, 5, 6, 7, 8. So you got 18 different hypothesis tests that you could work with. All right. Well, actually, some of them are confidence intervals, so not really that many. So kind of chop that number in half. So about 10 different hypothesis tests, but we're only going to learn about 5 of them. All right, the 5 most important ones. All right. So what we want is the one prop Z test. All right, that's option 5. Now just be careful, because if you're scrolling around looking for it, you might come across one prop Z int. If you're just looking for one prop, that could work against you because it just take you to the wrong thing. All right, so we hit enter on that one, and it brings us to this menu. And I'll talk about the characteristics of this menu momentarily. Now, some of your calculators are different, so you might not have the color blue part of it. And you might not have some of the options that are in the full-blown menu for stat tests. But that's okay because the 5 hypothesis tests that we're working on, they're on all the calculators. It's also one of the reasons why I chose those 5 to cover. All right. So anyway, what this is the interface that allows you to put in your relevant values from the problem that you're working on. Right. So whether it's test, problem, or project, these are relevant values related to the. What's that? Oh yeah. So like when I said that some of them don't have colors. So yeah, honestly, I've never even used that function anyway. I don't know what it does. My guess is it probably would, if we graph it in color, but we don't even graph them, so it doesn't even make a difference. So anyway, P sub O is going to be the null hypothesis. Now, the only thing that's going to be kind of tricky is the notation. The calculator, I'll just say flat out, is not really using the best notation. It's not using the best statistical notation. So we have to make an adjustment. We have to understand what the calculator is really asking. All right. But it's a quick adjustment because the other two values, the x and n, those are pretty easy to pull out of the problem. So number of successes and number of trials. So number of successes, number of trials. So just like a probability question, right? And in fact, this is a test of probability, right? Because we're talking about number of people who chose apples, number of people overall. What are my chances of the population agreeing with me? Really, that's ultimately what I'm going for. So this is the structure of this hypothesis test. Now we just have to tailor our work to correspond with that, right? And so what a lot of people have done in the past is, sometimes they completely whiff on which hypothesis test goes along with which study, and so they start clicking on different options. Like, all right, I'll try stat test option 2. Right? It doesn't have what I need in it because it's asking for means. I don't have any means. Stat test option 8. Same deal. This was 8. This is 5. Stat test option, anything else. It doesn't have the right structure or format, so we just keep going until you find the one that fits.
Is that success or successes?
Successes. So I'm going to set up my null and alternative hypotheses. It's asking, well, we have an alpha is 0.05, so I'm going to make a note of that. Test the claim that the majority of the population, actually, let me not underline the whole thing. What the flibbity flobbity flu just happened? Oh, I inserted the page for some reason.
Never heard that.
Yeah.
But now it's not 50%, it's 0.5.
Well, that's the alpha value, so that's going to be something different. Well, we're looking at majority, so that will be 50%. That's going to involve a 50%. If I can get my pen to work, I can actually write it. All right, so we have to state the null and alternative hypotheses. My Lord. That just takes too much effort to even write. So anyway, they're asking us to state the null and alternative hypotheses. I know that the null is going to involve an equal sign. The alternative is really going to involve mostly anything but an equal sign, but specifically greater than, less than, not equal. All right. Majority means greater than 50%, so greater than 0.5. All right. So because there's a greater than symbol, that becomes an alternative hypothesis. All right. So I'm going to make a statement that P has to be greater than 0.5. All right. So that's the population proportion. All right. I'm making a note of that because, I mean, it really kind of stinks, but P is one of the more overused letters in statistics. Because in order to understand the outcome of this study, we're going to have to figure out the P value, which is different from this P. This P is the population proportion of people who chose apples to be the most delicious fruit, but we'll worry about the language later. All right. So this is what I want to determine, right? I want to determine if this is true. I don't have a rooting interest. I don't really care. I mean, maybe somebody does care, because if you're a producer of apples, you'd like to know if people really do think apples are the most delicious fruit, because that's going to affect your bottom line, right? Same thing. I mean, you could apply this to anything else too. You know, like if you're producing anything, you would want to know if there's a demand for the thing that you're producing, right? The null hypothesis is almost exactly the same, except it's going to have an equal sign. All right, so I'm going to use the same values in the same order, but I'm just going to change it to an equal sign. All right, so these are going to be the same. That equal sign is there as a default. All right, so that's the not really a value, but that's the symbol we default to if it's not whatever is in the alternative, so greater than, less than, or not equal. Right? So if we can't say that it's greater than 0.5, we just say it's 0.5, right? Because just because we can't say it's greater than 0.5 doesn't mean we have enough evidence to say it's less than 0.5. I mean, we'd like to go truly with the opposite direction to make that opposite relationship exist between null and alternative hypothesis, but there wouldn't be really enough evidence to say that, because, I mean, to really conclude, well, the alternative is a majority, the null would have to be a minority. Well, I don't have enough evidence to say that it would go the other way, so we default to the 0.5, right? We just call it a 50-50, right? Basically saying, I don't know. All right. So, and that's kind of what you're going into the study with, the idea of, I don't know. That's why we're studying it. Right. So you collect data. You want to make a determination if apples are the most delicious fruit, but you don't really know. That's why you're collecting data. I mean, you might suspect, but you don't have any real evidence going into the process. So what we would say is, all things are equal going in. It could go either way. All right. That's the equal sign. The greater than is what we're testing, because once you collect, and sometimes, you know, you decide on what your hypothesis test is going to be after you've collected your data, because I really would have no idea going into this. But then I poll the 4,500 people, and I see that 2,475 of them said that they liked apples. They chose apples. All right. Now half of 4,500 is 2,250. All right. 2475 is more than 2250. So I'd look at it and say, well, for my sample, that's a majority. Now, does that correspond to the majority of the population? That's why we're doing this. Because you could look at this and say, I mean, legitimately, why are we doing this? 2475 out of 4,500 is a majority. Yeah, but that only allows me to draw a conclusion about that sample. I want to project it out to the population. I want to be able to say that this representative sample has characteristics of the population, so what's true for one is also true for the other. That's what a hypothesis test does for us. All right. So now that I know what the hypothesis test is supposed to be, I just need the stuff to put in my calculator. All right. So P sub O. All right. So this is the weird part, because P sub O, it's like, what the hell is that? I thought we had all this information here. All right. That is the calculator's way of identifying these values. These are the P sub O's. All right. P sub O is really an initial value, which we can when you use the sub-zero notation, because it's really a zero. I just say O because it's less syllables. But P sub 0 is the probability or the proportion at time 0. All right, so the starting probability, or proportion in this case. So before anything has happened, that's what it means to be initial. You're like, no time has passed. All right, so if we're thinking about it along those lines, then that would make it a default. All right, so an initial value is also a default value. Right? In physics, we talk about it all the time because you have an initial height of an object before you release it and let it drop or something like that. That's the default height. All right? If no time passes, that's the height that you're at. All right? It's only when time starts passing that's when the height changes. All right? So long story short, whatever value is contained within your null and alternative, that's going in for the piece above. The x and the n, that was in your problem. They told us that the number of successes, x, would be equal to 2475. And the number of trials, n, would be 4,500. All right. Now, sometimes it's not that easy to pick out which, conceptually what the number of successes are. But when you chose apples, you identified yourself as a person supporting whatever the claim is. So that could be defined as a success. But also, if it's part over whole, and you have two choices, x and n, the n is the whole, well, that's got to be the bigger number. So the other one has to be the x. Right? So x is always going to be smaller than the n value, right? Because it's got to be part of the whole. Right? So now we have everything to put into our calculator to get our p-value. So I'm going to put in the 0.5, the 2475, the 4,500, you have a choice between a not equal, a less than, or a greater than symbol. Our alternative hypothesis has a greater than symbol, so I'm going to hit enter on that option. And then I go right on down to calculate.
Back to that alternative, say that again, like alternative.
Alternative has a greater than, so that's the one we're selecting.
What happens to the calculator?
Oh, it just got blurred out because it's a blinking cursor.
Enter after that, right?
Yeah, then you just hit enter. Let's see if I can get it. Yeah, it keeps blacking it out. I don't know why. Try it one more time. Oh, I got it that time. There we go. So when you hit enter, you get this display. It's a interesting looking display. Some of it's repeated values, but in slightly different forms.
I didn't get the
So go back into the one prob z test. Yeah.
This is what I got. Because when
You have a not equal, it should be greater than.
yeah.
So stat,
Okay.
test.
5.
Yep,
Enter.
yep. You have to hit enter on that one.
Oh, okay. This.
Yep.
And then press enter.
Then hit enter, yep. Then go to calculate.
And then calculate and enter again.
And then enter again. And there it is.
Oh, now it's.
No problem. All right, so you look at all this stuff here, you're like, wow, this is a lot of work. But really, this was just getting you to the function. It's just a couple of keystrokes, typing in some values here, and then just getting to this. And all we need from here is the p-value, which, of course, the calculator doesn't really want to cooperate with us. Just calls it a p. All right, so this is p-value. All right, that highlighted number is the p-value. Yeah, so when you write a solution on a test or in a project,
Can you read out what the answer was?
this one?
Yeah.
P-value, yeah. Oh, the number?
Yeah.
9.906446. Yeah. So when you're writing a solution on a test or in a project, you just have to give me the null and alternative hypotheses, the alpha value, and the p-value, right? Because everything else is going to be embedded in the work that you do, right? So, I mean, it'd be nice if you gave me the x in the end, but you will, if you're doing a study, you will have collected data and you will have shared that data with me, so I'll already have seen that. If you're doing working on a test, it's going to be in the problem, so I already know what the values are. All right. So, bottom line is, I'll know that you did the process right if you have the correct p-value, because if you select the wrong, for example, inequality, then you're going to get a different p-value, and I'll know where you went wrong. Right. So it's pretty cut and dried in that regard. Right. It just seems like a lot of work because of all the notes that I'm writing, but it's really not. All right.
And we know the inequality because it says majority.
Majority, exactly. Exactly.
More than the 50%.
Correct. Right. So now we just have to draw the conclusion here, right? So that's going to go back to the template, but that one statement on the previous page, which was, and I'll write it here again, if the p-value is less than the alpha value, we reject the null hypothesis. So I talked a lot about theory before, but this is just, it's a fact. If the p-value is less than your alpha value, you reject the null hypothesis. So my p-value here is 9.906. I'm going to write the whole thing. 446. And it says e negative 12. That's the same as scientific notation times 10 to the negative 12th power. Right? I just want to know if that's less than 0.05. And I apparently cannot get my spacing down. All right, so I'm just asking, is this number less than that number? Well, if you have scientific notation with a negative exponent, it's a pretty safe bet that it's a very small number, all right? Because that number would be what this is if you move the decimal 12 units to the left, all right? So this would be 0.00000000099064446. All right, it's way less than 0.05. It's practically zero, right? So this is a true statement, so we reject.
So it says that any value is a negative power.
Negative power for your scientific notation, yeah. So therefore, I'm putting the three dots in the form of a triangle to mean therefore. Therefore, we reject the null hypothesis. And then we just have to write the conclusion, and then that's it for this.
My p-value is different.
Did you use a greater than symbol
Yep.
at the top of your screen?
It's 9.90644, then 5524e minus 12.
Oh, that's the same thing.
Negative 12.
Mine's just rounded.
And how can I round mine?
You don't need to. It's all the same. All right, so we're going to reject the null hypothesis. So what I do is I go back to my hypotheses, and I say I look at my two choices. All right, I got an HO and an HA. HO is the null hypothesis. HA is the alternative. I just concluded that I have to reject HO. So HO is bad news, so that gets an X. HA gets a check mark. All right, because it's one or the other. I just said that HO is no good, which means HA has to be the correct choice out of these two options. All right, so now I just have to write up my conclusion, knowing that I'm rejecting the null hypothesis. All right, so I'll snip my template here, and then I'll show you how to use it.
Where do you go if the p-value is smaller than success, right? The x, is that x?
Say it again, sorry.
See where you have
Alpha.
the p-value, where you go, yeah, right there.
P-value is less than alpha.
Alpha, okay.
Right. No problem. All right, so this is my conclusion template, and you're just following this. Now, one thing that you got to keep in mind is that, like I made the commentary before when we were talking about perception and grading and stuff like that, you know, tests and things along those lines. And I said if you showed me an English paper or, you know, English writing prompt, that I would say it was hard, and I wouldn't even really look at the question. It's just hard no matter what. Right? So with that in mind, this template is what I'm expecting you to use to write your solution, to write your conclusion. It may not always read in a way that is like a literary masterpiece. You know, you'll read it and be like, "Ooh, that's an awkward sounding sentence." That's fine, as long as you have the appropriate structure. You're going to be okay. I mean, more than okay. You're gonna get full credit.
Two sentences or just the highlight?
No. I mean, the highlight are the things that we're going to change within the sentence, but we've got to write the whole thing. All right. So, observe. There is. So, we had a choice of insufficient evidence or sufficient evidence to reject the null hypothesis. Well, we're rejecting the null hypothesis, so there is sufficient evidence. To reject the claim see where all my typos come from. I really can't type. That. Now we have to state the null hypothesis in words. All right? So that's where things get a little interesting, because most of the time they'll tell you in the problem what the null hypothesis represents, but sometimes it's not always obvious. All right? This is what I want in text color. So P is talking about population proportion. I thought I changed the color on this. Population proportion of, you gotta say what it's of, can't just say population proportion. People who chose apples as the most delicious fruit all right, so that's what the P represents. We never stated the rest of the null hypothesis. If that happened to be equal to 0.5, is 0.5. At the 0.05 significance level. So the population proportion of, that's P in general, but specifically in this problem, we're talking about people who chose apples as the most delicious fruit. All right, it's a little wordy, but that's because that's what P was defined as in the problem. But the language was in the problem for you, so it's really just copy. Therefore, the claim that, then we state the alternative hypothesis in words. Now that alternative hypothesis is a little different because you might say, okay, I'll just write the exact same thing, except I'll use, instead of is, I'll say is more than. But the question was talking about a majority, right? We got this greater than symbol from the fact that right up here, it said test the claim that the majority of the population finds apples to be the most delicious fruit. That's what my alternative was really talking about, and that's what I want to address. So, therefore, the claim that the majority of the population chose apples as the most delicious fruit. You're going to hate apples after this question. That's going to be a true statement. Now, I know from past experience that people have found it a little dicey, the whole sufficient, true, false, that kind of business. And people have said in the past that they've found value in the idea that sufficient corresponds with true. So, does it actually? I could just highlight it. Sufficient and true correspond with one another. When you're writing your conclusion, if you use the word sufficient here, you're going to use the word true there. Right? So they said that was helpful. I didn't even pick up on that until it was brought to my attention. They thought it was a good thing. So if it's helpful, then there you go. Right? But the process is always going to follow this template.
So the p-value 9.9 is greater than 0.5, right?
Less than.
Why is it less?
Because this is the same as saying 0.00000000991, roughly. So this is a very, very small number. This is less than 0.05, which tells us to reject the null hypothesis. Right? And because we're rejecting the null hypothesis, we can draw this conclusion. Now it's not the most user-friendly way to go about it, but there is a calculator approach for, I'll show you very quickly. There is a calculator approach for testing whether P is less than alpha. It's just, I found that people in the past didn't really like it. So I'll share it with you, but without any expectation that people are going to look at it and say, yes, of course, I'll use that from now until the end of time. All right, so you can call up the p-value on your calculator. You could also just type it out, but I find that calling it up is the better way to do it because then you don't have to worry about that scientific notation. So to call it up on your calculator, what you do is you go into the vars menu. So I'll do the keystrokes down here. You hit vars and go to option 5, which is statistics. Actually, that's probably a better snip. Then you go over to test. Any variable that's used in the test menu in any capacity is listed in this menu. So if I run a hypothesis test and I get the p-value, that first entry is going to be whatever that p-value is. So I would select that. All right. This is the part, that part isn't bad. This is the part that people don't like. Then what I would do is I go into second math. So second math, which is the test menu. All right, so I'll just make a note of this. second math, and this one is vars. Then I would select the less than symbol, option 5, which again, just like before, is probably a better snip, so let me do that. And the one thing is that it's always, because we're always testing whether the p-value is less than alpha, so it's always going to be this option, option 5. And so you just type in your alpha value, which in this case is 0.05. And then hit enter. So I think I pointed out 2 things that you wouldn't like, potentially. So here's the third thing that you're not going to like, necessarily. So you get a 1. You're like, what the hell does that mean? Fair question. All right. 1 means true. 0 means false. It's the calculator assigning probabilities to these outcomes. It's saying that this statement is true 100% of the time based on the information that it has, right? Or 0% of the time based on the information it has. So it's binary. So it's either going to give you a 1 or 0, true or false, right? In this case, it's saying that it's true that the p-value is less than the alpha, right? Because of that, we know to reject the null hypothesis, which brings us down this pathway in writing the conclusion, all right? Most p-values, it's very easy to see how it relates to the alpha, but sometimes there's some funky ones like this one where it's like, I just don't see it, all right? But a little piece of advice, actually a very, very big piece of advice, if you see a p-value that starts with a whole number, start looking for that scientific notation, right? Because if that p-value started with a 9, p stands for probability value. Probabilities have to be between 0 and 1. So how could it be 9 point anything, right? It would have to be in scientific notation in order for that to be true. So the reality is most people just kind of go by that and say, well, if I see a whole number here, that must mean scientific notation, which must mean that it's less than alpha, because that's always how it works out, so I'm not even going to bother testing anything, you know? So it's tricky stuff conceptually, but it's not overwhelming once you kind of get into a groove.